I will include explanations for how we get the data, how we train DNN with active learning. Let's get started with MATLAB simulation. We use MATLAB to get all of our training and testing data. In order to make our algorithm more integrated, we use Python code to enable Jupyter Notebook to activate our MATLAB algorithms through creating two .tmp documents to record input and output data points, and using subprocess library to activate MATLAB. We use randomly generated 3D latent dimension lengths as our input of simulation. And each of our output data looks something like this, so these three graphs make up one of our simulated data point set. The entire process of simulation goes through 3D simulation and a projection from 3D to 2D. Then the algorithm produces a velocity map and a according drag coefficient. Firstly, we use Navier-Stokes equation to produce 3D environment for the fluid dynamics system. The equation includes all of our listed variables in the legend section, which stands for each element of a fluid environment. As is shown in the 2D demo, the way we make our simulation is to fit BSP lines based on 3D dimensional lengths. Smooth curves are drawn around those dimensions to create an object. Then we map the 3D shape into 2D. We achieve this process by creating a geometry that represents the object in its relevant boundary conditions. Then we create a mesh to represent the state of each point of the system. We use a MATLAB add-on called QuickSim to fulfill this conversion. At the same time, we convert the mesh condition map into a color-coded map that represents the relative velocity of each point. Those velocities are shown by the color bar on the right side of the graph, such that the relative velocity of the environment in contrast to the object is revealed. Finally, we apply this equation to calculate the drag coefficient of the object, given the information provided at the time of simulation. For this specific case, the drag coefficient is calculated to be 0.41408. The second thing we need to do is to fit a trend to predict resistance. To do so, we use the deep neural network because of its flexible function family and ability to capture hidden relationships between each input. Specifically, we have the fully connected layers denoted by the equation at the top, with W being weight, X being our input, and B being bias. W and B will be our training parameters. We use value as our activation function. For selecting specific methods of training, we compare the performance of different models. Here, we take CNN and DNN for examples. Because we have quite characteristic traits for our velocity graphs, as different colors stand for different velocity, which is a substantial factor of the drag coefficient. This may naturally lead us to think about using CNN because of its popular method. It's a popular method that model regression directly from 2D images. However, although this method deals with the reduction of human domain knowledge, we will still need to simulate a huge amount of data and train with more computation costs because of its two-dimensional nature. The sample size would exceed hundreds of thousands, in fact. That's why we choose to use DNN, which will avoid such a computation burden with its numerical input. To extract such numerical inputs, we create latent dimensions on the 2D object by dividing them into 8 pieces. Then take 4 of its representative dimensional lengths as our input number array. These 4-dimensional arrays become our training input to build a deep neural network architecture as this. We have compared architectures of different layers and different neuron numbers of each layer. This architecture optimizes the regression performance. Each layer is connected through the fully connected equations is represented on the bottom right. Each input dimensional data is convoluted by 5 layers of weights and biases, which are trained variously to achieve optimal performance. The third, and also the last thing we will include in our study, is active learning. This is used to further reduce the number of data points needed. Its ideology is originally to input limited amount of data and have machine-raised unlabeled data points for further information provided by human experts. However, in our case, we realized that our model would raise only predictable decisions for humans to make, so we designed two loops to avoid human inputs in this process. The first cycle is to ensure the model is being trained optimally without human input in adjust parameters such as training steps and epoch. We have machine enumerate through all possible parameters on their own discretion. For example, the only possible range of the training step is from 10 to the negative 1 to 10 to the negative 5. So this only has to enumerate 5 times as a maximum. This ensures that our model finds the least possible mean square error prediction. The second cycle judges if our model is going to retrain itself. This happens when our fitting does not find the optimized shape. This judgment is done simply by comparing the predicted optimal case with previously existing data points. One thing worth mentioning is that in order that our model does not miss the most optimized shape, the model will retrain itself for one more round even if the predicted case is smaller than all the previously existing cases. This active learning process can be visualized by this demo. For the purpose of visualizing it, we ignore 2 of the 4 representative dimensions and only leave width and height. Then we project the drag value onto the z-axis. As we can see from the graph, the optimal shape predicted by the plane fits the trend in the first round of training shows a shape that is not all that optimal. Of course, this is captured by our mechanism so that the newly produced shape is included into the training dataset and have our model retrain itself. Such process will continue until optimal shape, as shown on the top right, is secured.